Okay, so this review is going to be all about derivatives. We'll try to cover bases for both professors. Okay, so we're going to compute some partial derivatives using the very definition of partial derivative. We're going to compute directional derivatives using the definition and some formulas. And then we're going to discuss what it means for a function to be differentiable. Specifically, we're going to talk about how the existence of partial derivatives does not guarantee the differentiability of a function. Okay. And we'll talk about the sufficient conditions for differentiability, those being that the partial derivatives are continuous. So then we're going to compute derivatives for functions from Rn to Rm, maybe look at a chain rule example, and we'll go over linear approximations and tangent planes. All right. So let's start with partial derivatives. Okay. So let's just look at an example of a function of two variables, just to see how it's done. Okay. So the partial derivative of a function with respect to the first variable, x, at a point, is defined by like a one variable type of derivative definition, but where we only vary one variable at a time and keep the other variables constant, fixed. So here I'm taking a derivative with respect to x. So I'm going to let h go to 0, and we would evaluate the function at x plus h, because it's x that we're going to vary, and y is going to be fixed. And then we find the difference between the function at x plus h y and the function at xy, and divide by the change in x, which is what we call h. Okay. So more generally, if you have a function from Rn into R, the derivative of the function with respect to the ith variable would be a limit as h goes to 0. And the way you write this would be to say that I'm going to evaluate the function at x plus h, and then times the ith elementary column. So that would be where it's all zeros, right? Except the ith entry is a 1. Minus the function at x, and then you divide by h. Okay. But it's useful to do a simple example, say from R, in this case from R2 into R. Okay. Let me look at chat. Okay. So in this problem, I'm going to replace x with x plus h. Leave y alone, and then we get x squared, so that's x plus h squared. So that's this part right here. And then we subtract the function at x and y, so that's just rewriting the function. And then we divide by h. So you just multiply this business out. And if you're doing things correctly, you're going to get cancellation so that you only have terms that have an h in them. So let's see. x times y minus x times y, x squared minus x squared. And indeed, we only have terms that have an h in them. So that's convenient because then when you divide by h, we have a cancellation. Okay. So now we can easily take a limit. Before if we had tried evaluating the limit here directly, we would get 0 over 0. But now that the pesky h in the denominator canceled, we can let h go to 0, and we're left with y plus 2x. And I'm sure that you're familiar with taking partial derivatives. Right, so we just differentiate x times y with respect to x, and differentiate x squared with respect to x. So we indeed get the same result, whether we do it by definition or by the rules for partial differentiation. All right. So now we would say that for this function from R2 into R, there's a matrix of, let's write it this way, there's a matrix of partial derivatives. It's called the gradient of the function. So this is in general, it's a gradient there's a gradient for functions from Rn into R. If the partial derivatives exist, the gradient we can define to be a matrix, let's say a 1 by n matrix, whose components are the partial derivatives with respect to the coordinates. So in this case, this is just going to be the partial of f with respect to x and the partial of f with respect to y. And we already computed the derivative of f with respect to x. And we could use either definition or formula for computing partial derivatives to get the partial derivative with respect to y. So that would be just x. Okay, so this is the gradient. It's just this vector of partial derivatives of your function with respect to the coordinates. Okay, and then as you probably learned in lecture, if it turns out that the function is differentiable, which is different than the existence of partial derivatives, then the derivative of this function at xy would be this matrix, right? So that's also, in this case, our function is differentiable, just a bunch of polynomial-like stuff. So this gradient coincides with the derivative. Yeah. All right, so next there's something called directional derivative. Partial derivative is in fact a directional derivative. So if I'm differentiating a function with respect to x, I'm finding a directional derivative of the function in the positive x direction, as we're moving in the positive x direction. F, before f. Are you referring to this symbol? That is the derivative of the function. So depending on the professor or book, you'll use different notation, but in multivariable calculus, I find it convenient that if you're defining derivatives from Rn to Rm, it's just best to use the derivative of f using that notation. because the derivative in general is going to be a matrix. So like, so maybe derivative of f at a point, right? So at, so it's a little confusing, but at a point. If your function is differentiable, this derivative will turn out to be a matrix consisting of partial derivatives of the components of your function. Yeah, but anyway, derivative. Okay. So just a quick distinction still. So you'll be asked to compute gradients, and that's just a vector with partial derivatives in it. And if the function happens to be differentiable, that will be the derivative of the function. Right? So it's possible that partial derivatives of a function exist, but the function itself is not differentiable. So there's a slight nuance. Okay. All right. So next we want to define directional derivative. So here the idea is that you have some function from Rn into R, and you want to know the derivative of the function as if you're in the domain, that's Rn, and you're at a point, let's say AB, or just we'll call it A, and you're moving into as you're moving in the domain in a certain direction as pointed by vector v, you want to know the rate of change of the function in that direction. Okay. You want to know the directional derivative. So we write the derivative of the function at point A as we head in the direction of vector v. Okay. And this is defined again as a limit. So this is a primary definition. So we're going to let t go to 0. And we're going to evaluate the function at A plus some multiple of this vector, right? So, well, let me finish writing this. So minus the function at A divided by t. So this part is just what the function's value is at point A. And this part would be what the value of the function is a little bit removed from A in the direction, right, as a multiple of, right, so you're finding the value of the function at the orange point and then at the green point, and you're finding the difference, so the change in the value of the function, and you divide by t. Okay. Now, if the function is differentiable, then, so let me make sure I write that. If f is differentiable at A, then there's a computational formula you can use to compute directional derivative. Then it's just the gradient of the function, or the derivative, if you will, times v. So this is a triangle for gradient. It's the del operator. And this is the direction vector. And so you can think of it as a dot product as well. I tend to think in terms of matrix multiplication, so I don't usually write dot product, but it's a dot product, if you will. Okay, so let's look at an example. We'll use the same function as before. Apologize for that. Okay, we'll use the same function as before. And we're going to find a directional derivative, let's say, of the function in the direction of the vector 1, -1. At the point, let's say 1, 2. Okay. So there's 3 things that you're coordinating: the function itself, the point at which you're going to be finding the directional derivative and the direction vector. Okay. So you write the directional derivative of f at the point 1, -1 in the direction of vector v. Made a mistake. Okay. See, I was trying to warn you, and then I made a mistake. So it's the directional derivative of the function evaluated at 1, 2. So x and y are 1 and 2 respectively. And the vector that gives us our direction is the vector 1, -1. Okay. So this function is differentiable. So let's first just use the formula. So that's going to be the gradient or the derivative of the function, because this function is differentiable at 1, 2. Dot it with the vector v. Okay. So we already computed the gradient of this function. It was this vector of partial derivatives, the derivative with respect to x. Then the next component is the derivative of the function with respect to y. And we're evaluating this at this specific point. So at the point 1, 2 times sorted with the direction vector v. Okay. So y is 2, x is 1, so we get 4, 1, dotted with or multiplied by the direction vector, so we get 4 minus 1. So the directional derivative is 3. You just get a number out of it, right? Because you get like a sort of, well, if the direction vector were a unit vector, you would get the rate at which it is changing in the direction of the direction vector v. Okay, so that's the computational formula, right? So you probably, in Cohen's class, you probably learned this as the gradient dotted with direction vector. Okay. But we can also use the very definition. So this is using the definition. We should get 3 again. So the directional derivative of f at the point 1, 2 in the direction of vector v, which was the vector 1, -1. So that's a limit as t goes to 0. And here we're going to evaluate the function at the point 1, 2 plus a little perturbation away from the point 1, 2 in the direction of vector v minus what the function is at the point 1, 2. So that gives you the change in the value of the function between 2 points. And then we divide by t. Okay, so let's see. So the function, again, what was the function? It was xy plus x squared. So we get x times y. So x we see is 1 plus t. Then times y, which is 2 minus t. And then plus x squared. So that's x is 1 plus t. So 1 plus t squared minus the value of the function at 1, 2. So that's 3. We just multiply the business out. Okay, so that was all of this. And then minus our function at 1, 2. And just because, you know, a partial derivative with respect to x or y is just a directional derivative in the positive x direction, y direction, similar mechanics should occur, right? Where all the stuff that doesn't have a t will cancel. So you're only going to be left with terms that have a t in them, which will conveniently cancel with the t in the denominator. So let's see, we get let's see, how many t's do we have altogether? 3t. and t squares, the t squares happen to cancel out, so nice. Okay, so that's easy. Gave myself way too much room there. The t's will cancel, and we're left with a limit of a constant. So again, we get 3, using the definition of directional derivative. Okay. All right, so I'm trying to think of what I want to talk about. Okay, let's talk about this idea of a function being differentiable. And that's not the same thing as saying the partial derivatives exist. Okay, so we say a function is differentiable if, so we say the derivative of function at x exists if the following limit is 0. So we have a limit as h goes to 0. That's a vector in general. And you have the value of the function at x plus h minus the value of the function at x. Okay, and so this is the change in the value of the function. And if there's a linear approximation, so let's call it L, or, did not mean to do that. Let's call it big L. So this is a linear function on h. So if there exists a linear function on h, not on x and y, but on h, at our point, then if this limit is 0, then we say that this derivative exists. Okay, and the derivative will be this linear function. Right? But let's look at an example. Let me pull it up in my notes of a function whose partial derivatives exist at a point, but which is nevertheless not differentiable. So that's a standard kind of problem to emphasize the fact that the existence of partial derivatives does not guarantee differentiability. So here's the example. And this example will use the definition of partial derivatives to find the partial derivatives. And also a fact that you, Professor, I'm sure told you about. And it's the fact that if a function is differentiable, so this is important in this example, it's key, at a point, of course, then f is continuous at that point. Okay, so this means that if your function turns out to be, so this is the consequence that we're going to use. So if f is not continuous at a point, then it cannot be differentiable at that point. Okay. All right, so here's the example. It's a example of just a real valued function on 2 variables. And it's defined by, let's say, xy plus y cubed divided by this business. Okay, and we're going to discuss, we're going to show that the partial derivatives exist at the origin. So we're going to be focusing, let me just say it's, so this is when we're away from the origin. And let's just define the function to be 0 at the origin. Because otherwise it would be trivially discontinuous and that would be no fun. Right, if the function is not defined at a point, it can't be continuous there. L is L just represents some linear transformation, to answer your question. It's just some linear function on H. I'll show you examples of how to, what that is. But it's going to turn out to be the derivative that you're looking for. Sorry, so this is wrong. This is the derivative exists if this limit exists. Okay. It just turns out that this L will be the derivative of the function at a point. And its job will be to operate on H. So my bad, this is not equality. I meant to say that the derivative of the function exists at a point if this limit exists. And it turns out and this linear function will turn out to be the derivative. Okay. So sorry about that. All right. So do the partial derivatives exist at the origin? Well, let's just use the definition, right? So the partial derivative of f at the origin with respect to x for now is a limit as h goes to 0, and here we're going to evaluate the function at 0, 0 plus h 1, 0. So these are actually really simple. Right, so remember the partial derivative with respect to x is just a directional derivative of the function as we go in the positive x direction, so in the direction of vector I, not j. Okay. All right, so we have, so it looks like y would be 0, and x would be equal to h in that case. Right. So this is really h0 if you add this up. So we get h times 0 plus 0 cubed, and then we get h squared and obviously that we just get a limit of the constant 0. So we get 0. So indeed, the partial derivative of the function at the origin with respect to x is 0, so it exists. That limit exists. So similarly, we can show that the partial derivative of f with respect to y evaluated at the origin so this time it's like a directional derivative in the positive y direction. Okay, so now it looks like x is 0 and y would be equal to h. So going back to the definition of our function, right, we're going to evaluate this at 0h. So I'll plug that in. X is 0, y is h. Okay, my function at the origin, which is defined to be 0. Oh, I forgot. Oh my gosh. One second. I forgot to, okay. I forgot the rest of it. So apologize. So this was just this part. I forgot to subtract the value of the function at the origin, which was defined to be 0, and then divide by h. So the result doesn't change. we still get the limit of 0 divided by h squared as h goes to 0, but 0 over h squared is 0, so that's 0. I forgot the full thing. That is so terrible. I apologize for that. So this was this, and then we had an h in the denominator. And that reduced to, after plugging everything in. Okay, so same thing, right? So now the function at the origin was defined to be 0. That came from this piecewise definition. And then we divide by h. That's from the denominator here. All right, so we simplify and evaluate the limit. So it looks like we have h cubed divided by 2h squared minus 0 divided by h. All right, anyway, we get 1/2 h divided by h. So the h's cancel, and when you take a limit, you get a half. So the partial derivative of f with respect to y at the origin exists. It's equal to 1/2. Okay. And now the existence of these two partial derivatives does not guarantee the differentiability of the function. And we're going to show that the function is not differentiable in that kind of indirect way by showing that the function is not continuous. Therefore, it's not differentiable. And so you already know that for a function to be continuous, the limit has to exist. Okay, so let's show that the limit doesn't exist by maybe. All right, we're going to show that this limit does not exist. That does not exist, which will imply that the function is not differentiable at the origin. Okay, so looking at the function, I'm just going to try a line. So I'm going to try to, well, let's try the, let's say, x-axis, right? So let's take the limit as we approach the origin along the x-axis. So that means that y would be 0. So x times y. So I'm just now replacing y with 0 in the definition of the function. And hopefully you see that, well, it's clearly, so this is equivalent to x going to 0, turning this into a one variable problem. Then you get 0 over x squared. So that's a constant 0. So the limit of a constant is a constant. So approaching the origin along the x-axis, we get that the limit is 0. On the other hand, if we approach, say, the origin along a line like y equals x, so now we're going to let y equal x, all right? So I'm just going to, in the definition, I'm just going to replace y with x. Okay. Plus, so y cubed becomes x cubed. You get x squared plus 2y squared minus. Okay. And again, I'm just plugging everything into the definition of the function, which was this. You know, every y became an x. So this is the expression that defined our function. Okay. And we're going to the origin, of course. So we get limit as x goes to 0. And in the denominator, these cancel. You get 1 plus x. So after simplifying and letting x go to 0, at the limit we get 1. So because we had, depending on the approach to the origin, we had two different limits. Yeah, 0 does not equal 1. The limit doesn't exist in general. Okay, so we've showed that the limit does not exist. And therefore, the function is not continuous, so it cannot be differentiable. Okay. All right. So what can we do next? Well, I think for the sake of Dr. K's class, we might want to compute some derivatives. All right. So let's assume that, okay, we have a function from Rn to Rm. Meaning that our function has n inputs and the output vector has m outputs, right? So you have coordinate functions, f1 at x, f2 at x, all the way to fm at x, m outputs. And it turns out that if the individual coordinate functions, each of these is differentiable, then the whole function is differentiable. And the derivative would be given by a matrix of partial derivatives. So the derivative of the function at x will be a matrix, which is m by n matrix. And we know that because it's the number of rows is the number of component functions, and the number of columns is the number of independent variables. Okay. And what we do is just compute the derivative of the first component, so f1 over here, with respect to all n variables. So derivative of f1 with respect to x1, derivative of f1 with respect to x2, right? And we keep going until we exhaust all the independent variables. So the last partial derivative will be derivative with respect to xn. So that's 1 to n columns. Okay. And we have to do this for all m components, right? So then we take the derivative of the second component with respect to x1 and repeat the process with respect to x2 and so on. And if you do this for all m components, you're going to end up with 1 to m rows. Okay. Right, and you get your m by n matrix. We will definitely do some chain rule, since you asked. Okay. So if your function turns out to be differentiable, that linear operator in the definition that acts on h is this matrix of partial derivatives, right? It is equal to this, where this would multiply, the way this derivative acts on h is by multiplying h for functions from Rn to Rm. So it's a multiplication, right? You would get like times h, where h would have as many components as there are input coordinates. I didn't mean to do that. Okay. So this derivative would multiply the column vector h1, h2, all the way through hn. Okay. So let's just do an example. Yeah, okay. So here's a function from R2 into R like we just did. We have x1, x2, or x and y if you wish, and the output is an R, so it has a single component. So the derivative of this function at x1, x2 is going to be what size matrix? So 1 by 2. So 1 by 2, and the components of this 1 by 2 matrix will be the derivatives of your one output component function with respect to x1 and x2. It's exactly like the gradient that we did in the previous example. So the derivative of f with respect to x1, that's 0. So the next component is the derivative of your function with respect to x2. Okay. So that's this kind of matrix idea matches your idea, the gradient we did previously. So a more interesting thing might be an example where we have a function from R2 into R2, say. Let's just use x and y. I get tired of subscripts. Okay. So this is your first output component for your output, and this is your second component for the output. Why 1 by 2? Because we anticipate that if your function is differentiable, the derivative is a matrix of partial derivatives, where the size of the matrix is given by m, which is how many output components you have, so m rows by n columns. Okay. So this is here we did an example of a function from R2 into R1. So the derivative matrix will be 1 row by 2 columns. Okay. So here, if we this function is differentiable, all the components clearly are differentiable. So the derivative of g at a point xy is going to be a 2 by 2 matrix. Where we differentiate the first component, f1, with respect to x and then y. And then we differentiate the second component, f2, with respect to x and y again. So this is derivative of f1 with respect to x, then with respect to y, x and y. Okay. So it's not surprising that this derivative is a constant matrix because this is a linear transformation. And the derivative of a linear transformation is just the transformation itself. It's kind of like y equals 5x. The derivative of y with respect to x is just the 5 itself. So you want to do chain rule, huh? Okay. Let's see. All right, so chain rule. Let's clear all this. Is useful. So I guess we can do this example where f is going to be a function from R3 into R2, defined by x squared y plus z and x squared plus y squared z cubed. Okay. And maybe we can make g a function from, let's say, R3 to R3. It's defined by a function of three coordinates, r, theta, and w. You probably see where this is going. Cylindrical coordinates, so the output is going to be r cosine theta, y, then we're getting r sine, and then w. All right, so, and what I'm going to do is create a new function on R3, which is defined to be the composition of f with g at this point. So that is to say, we take g and evaluate it at this point. We take the result and we plug it into f, right? So it's a composition of functions. So if you want to see what that would look like, we would get, okay, this would be like, the first component is like x, the second component is our y, and the third component is z. And you would plug that into, because you're composing into that function, so you get x squared times y would become r squared cosine squared, because that's x squared times y, plus z, and z is equal to w. And then the next component over here, x squared becomes r times cosine squared, and then y squared times w cubed. Okay, so we composed the function, and if we wanted to, we can now just find the derivative of h directly after doing the composition. And so we would differentiate the first component. So just to know, what's the size of that matrix, by the way? So the derivative of h. I'm going to diagram this out. So here's R3, here's R3, here's R2. Okay. So what G does is takes a point in R3 with coordinates r, theta, w, and maps it into another point in R3 with coordinates x, y, z. Then function f picks it up and returns a vector in, let's say, call it uv, in R2, because the output has two components. So the composition then, so the h is the composition of f with g. So g, you first use g and then use the result to plug into f. That's going to be a function from R3 into R2. So the derivative matrix is going to be 2 by 3 after the composition. Okay. But you can see that over here, right? H has 3 inputs, independent inputs, and then 2 coordinate functions for the output, so into R2. So this derivative we anticipate will be 2 by 3. All right. So let's differentiate the first component function with respect to r, theta, w. So with respect to r, you get like 3r squared. With respect to theta, and then with respect to w. And you do the same thing for the second component, differentiate the second component of the output with respect to r theta w. Okay, and you get something. Yeah, I guess, yeah, I don't want to waste time doing this because I was going to try to make a point, but anyway, you get some other components here. Okay, but so you know what the product rule does, right? So instead of the product rule is used for composition, finding the derivative for a composition of functions. So instead of actually doing the composition like we did and then differentiating the result, the product rule can be used to so the derivative of h is the derivative of the composition of f with g at a point. So the product rule says you differentiate the outside function. So remember, this is f composed, and g is inside of f, if you will. So the outside function is f, so you differentiate f, and you're going to evaluate that at g. And then you multiply, in terms of matrix multiplication, by the derivative of the inside function, g. So it'll be the derivative of g at the point. All right. Okay, so let's look at f again. So f is, so what's going to be the size of the derivative of f? What size matrix will it be? Let's make sure everybody's a presenter. All right, so I don't know if that, okay, it's 2 by 3, right? Two outputs, 3 inputs. And what's the derivative? What's the size of the derivative? What's the size of the matrix, which is the derivative of G? This is a basic kind of like cylindrical coordinate transformation. Okay. Well, this is a function from R3 to R3, as we mentioned, so the derivative will be a 3 by 3 matrix. Okay. So this matrix multiplication will be defined. All right. So let's compute the derivative of f. So we know it's just the partial derivative of the first component with respect to x, and y, and then z. Then the next row is the derivative of the second component with respect to x, y, and z. The derivative of g differentiate the first component with respect to r, theta, and w. The next one, and so on. With respect to r, theta, and w, and with respect to the third component, derivative with respect to r, theta, and w. By the way, this is this is called a Jacobian if you have a derivative, a matrix of partial derivatives from for a function from Rn into Rn. So the dimension of the domain matches the dimension of the codomain. And this determinant, you'll find this would be R. If you compute the determinant, you just get R, which is going to be important in when doing change of variable and integration. But anyway, that's neither here nor there. So let's get rid of that. All right, so now when we do the derivative of this composition, so H, we would multiply the derivative of F, but we're going to evaluate it at G, and then times the derivative of G. Right, so you take the derivative of F, but you replace X with, well, X is R cosine, so you get 2X times, and Y is R sine, X squared, that's a constant, 2X, 2 times Y times Z cubed. Okay. So you have to, if this, you don't write this down, you have to evaluate what X, Y, and Z are by looking at G. That was so badly worded, I'm embarrassed. Okay, and then times G. And if you multiply this, you would get the derivative matrix for H. All right. All right, so what was next? Right, so I think this next examples of differentiating will be good for both classes. So we're going to look at functions, let's say functions of the magnitude. Well, okay. Suppose you have the identity function. So you take a vector in Rn, and it returns another vector in Rn that is exactly x, right? So it's the identity function. Okay. What the derivative of this function is going to be what size matrix? What's the size of this matrix, which is the derivative of our function? N by n. Very good. Okay. And if you had to guess, what do you think this matrix will be? Since we have an identity mapping. That's supposed to be the I matrix, right? Okay, good. It's the identity matrix itself. So it's just all ones in the diagonal and 0 otherwise. It's the n by n identity. Okay. And now let's just see why this is true, right? So our input has n coordinates, and the output is exactly the same vector. So when you differentiate, right, we're going to take the first component and differentiate it with respect to x1. So we get 1. The derivative of x1 with respect to x1 is obviously 1. And then the derivative of x1 with respect to 2, some sort of kind of dyslexia-like thing happened there. So the derivative of x1 with respect to x2 is next, and that would be 0 because x1 and x2 are independent variables. And so on. The derivative of x1 with respect to x3 is 0, and so on. So the next row in our derivative matrix would be the derivative of x2 with respect to x1, with respect to x2, with respect to x3, and so on. So it's the identity. Okay. All right, well, that's not a very exciting example, but I hope it's kind of satisfying that the identity function has a derivative matrix, which is the identity matrix, yeah? Okay. So now let's look at, I'm looking at very basic examples here. So next we're going to look at a function from Rn into R, where the output is a number which is the magnitude of your input. Okay. So this is a good one to know for everybody's homework. Okay. So we know that this is the square root of x1 squared, so it's just a regular old norm. Squared. Okay. And so the size of this derivative will be 1 by n, where the first component is the derivative of our function with respect to x1. Right, so if that's your f, right, let me get the first component, second component, differentiate f with respect to x2, and so on. And just by the symmetry of the situation, if you know how to differentiate f with respect to just one of the variables, you know how to do it with respect to all of them. So let's differentiate this with respect to x1, the square root of something. We know its derivative is 1/2, and then in the denominator, right? So yeah, just to make sure, all I'm doing is essentially a chain rule here. That's u to the 1/2. So we can use the power rule for derivatives. Right, so then I multiply by the derivative of the inside, and I'm differentiating the inside with respect to x1. So I'm just going to get 2 times x1. Okay, and then, so I'm just using this rule, right? The derivative of the square root of something times the derivative of the thing we were taking the square root of. So if I do this with respect to x2, I would get 1 over 2 times the square root of, and then on top I get the derivative of the inside with respect to x2, and so on, right? And the thing would look kind of similar for all the other components. Okay, so we notice the 2's cancel out, and we can factor out the denominator as it's a common factor in all the components. And we're left with x1 ... all the way through xn. So in short, let's see what this is. Well, this denominator is exactly the magnitude of your input vector, right? And this is exactly your input vector, but transposed. Okay, so it's convenient to know that the derivative of the identity function, sorry, not the identity, of the magnitude of x is x itself, but transposed. If you follow the rules of derivatives, it has to be a 1 by n matrix divided by the magnitude of x. All right. Let me look at my notes. Okay, so as an application, not an application, but you can take advantage of this if you have, for example, a function of the magnitude of x, right? So let's say we have natural log of magnitude of x. Of course, defined for everywhere except the origin. All right, so you can think of this as a composition, can't you, right? So you think of like f of u being natural log of u. And then g of x is the magnitude of x, right? So f is a function from R into R. A certain subset of R, I should say, is the domain. G is a function from Rn into R, because you get a real number when you find the magnitude. All right. So I can think of this natural log function of the absolute magnitude of x as really a composition. Let's call that h. It's f composed with g at x. So f, so f is the log function, and inside we have g of x, which just gives you the magnitude of x. So indeed, that's the. But the idea is that if I think of this as a composition, I don't have to like think of this as, okay, I could, maybe good for practice. I write it out like this, and then find the partial derivative of this with respect to x1, and then x2, and x3. It's doable, right? So, sorry about that. Right, so if we did find the derivative of this function in that fashion, well, we would probably take advantage of the fact that this is log, so bring out the square root as a power of 1/2 you can bring in front. And you can differentiate that with respect to x1. So the derivative of log of anything is 1 over that thing. And then derivative with respect to x1, right? And so on. You can, and by symmetry, you would get similar stuff. So you could do it that way. And what you're going to get is, after the 2's cancel, you're going to get 1 over, I'm pulling this out, it's a common factor in all the derivatives. That's the magnitude of x squared times x transpose. Okay. However, I could think of the chain rule, right? Right, we think of this as a composition, so the derivative of h at x is the derivative of f at g of x times the derivative of g at x. So product rule. Now, remember what f is, right? We said f is natural log of u. So when you differentiate that, you just get 1 over u. But of course, we're going to evaluate that at g of x. Okay. Then times the derivative of g, but g we said was the gives you the magnitude of the input vector, and we already computed the derivative of that. We said that that's equal to x transpose divided by the magnitude of x. All right, so then we have that g of x is the magnitude of x. And indeed, we get the same result for the derivative of this, the derivative of natural log of the magnitude of x. This is the same result as this, right? Okay. And of course, Dr. K being Dr. K, there's some tougher ones as well. So let's look at an example. Let me just clear this out. We have a few minutes, so a tougher example might be for a function from Rn into Rn. Let's say it's defined by a scalar part times the vector part. Oh gosh, we don't have too much time to do this like component-wise, but you could, of course, think of this as x, the vector, times the magnitude of the vector. Right, so the vector x has the n components, but it gets multiplied by a scalar, namely the magnitude of the vector squared. So this is multiplication. And so you could get your n by n matrix by finding a pattern, right? You would differentiate the first component with respect to right, so this would be an n by n matrix, and you differentiate this component with respect to x1, so you would get 3x1 squared plus x2 squared, sorry, not, yeah, plus. Yeah, and then you would differentiate the result with respect to, so that's the first component. Then you differentiate the first component with respect to x2 and so on, and so that's a little painful, right? I'll probably use product rule on this. And then with respect to x3, and you probably see a pattern. Okay. Differentiate the next component with respect to x1, x2, x3, and so on. And so maybe you can spot a pattern there, right? So that's always one option. You have to do this. But here you can use a product rule. So what's the product rule? Well, if you have a function of, you have a scalar valued function, right? times x. You can actually use a product rule where you're going to leave x alone and then multiply by the derivative of the first factor. And here, because these are matrices in general, the order matters, right? And then plus, right? So here I differentiated the first factor, but when I multiply, I switch order, and then plus. Now we're going to differentiate x. So we're going to leave the first factor alone, but differentiate the x. Okay. So right, the function at x was the magnitude of x squared. So the derivative of this function, if I use the chain rule, is the derivative of something squared times the derivative of the inside, and the derivative of that oh yes, sorry. So that's bad. It's the derivative. So derivative of something squared times the derivative of the thing that's being squared. So that's the magnitude of x. And we know that the derivative of magnitude of x is just x transposed divided by its magnitude. We derived that formula. That's why I started with kind of one of the basic examples. It's good to know for the problems. Okay. So it'll turn out that the magnitude of x is canceled, and you'll get x times the derivative of f, which is 2 times x transpose, plus we left f alone, and the derivative of the identity function. Yeah, the derivative of x with respect to x essentially is identity. Okay. So for example, if I want to evaluate this derivative specifically at suppose specifically at the vector where all the components are 1s. Okay, then I would get x is just a vector full of 1s. And this is 2 times x transpose. And this is the magnitude of x squared. So what's the magnitude of x? Well, we have n components, all of which are 1, so that's going to be square root of n. So magnitude of x is just, magnitude squared is just n. So this becomes n, and this is the identity. Whatever. Yeah. So Dr. K kind of, you know how it is. You got to find a pattern. So we're just going to get, this part is just a matrix of all 2s. I think I got to go really soon. And then plus, and this is just a diagonal matrix after you multiply by n, where the diagonal entries are all n. So at the end of the day, you get a nice formula. But if you have questions about how to use the product rule, especially for functions, a product, we have a function of x, I guess I should say the magnitude of x times x in the homework. Right. So again, that was x times the derivative function plus you leave the first factor alone and differentiate the x, so that's like the identity mapping. Oh boy, this is complicated matter, right? All right. So that's, I think we're 6 minutes over, so there's somebody else coming in. But thank you, that was enjoyable for me. I hope it was. All right. Good luck. See you in the lab.